So the definition of resilience, so this is one of the definitions, the ability to return to the original form or position after being affected by a particular alteration. Or the ability to recover from illness, depression, adversity, or the like. So that's the definition of resilience in the general sense. So let's look at how we can apply this, or how we can get inspired by these concepts and apply them to software. Why should, as a developer, why should we bother about resiliency? Right? So resiliency should not be an afterthought. Resiliency should be something that we think about as developers from day one, right? So even if you're writing a simple web app that connects to a database, right? Like a typical mistake that developers make is, you don't think about, the database connection going down. So if your database connection is dropped, will you have to restart your application, right? So resiliency shouldn't be an afterthought. From day one, we should be able to think about these failure conditions, and we should have the tools and patterns and mechanisms to recover from these failures, right? So how can we have these concepts in a programming language so that, when you're writing the code on day one, the language itself sort of helps you in that direction to write resilient programs. So availability is critical in production. So these are some of the definitions of availability. So it's mean time to failure divided by mean time to failure plus mean time to recovery. So how can we increase availability? So one of the ways of increasing availability is increasing the mean time to failure. So make your software components as robust as possible. So that's one way of increasing availability. But beyond that, failures are going to be a part of life, right? So beyond a certain threshold, it will be very costly to increase the mean time to failure. So another way to increase availability is to reduce the mean time to recovery. So you basically accept that, okay, failures can happen. So how can we recover as soon as possible when systems fail? So again, that's another way to increase availability. So failures are a fact of life. So we can't avoid failures, so we have to embrace them. So how do we work with failures? So when it comes to software, resiliency is the ability of an app to recover from certain types of failures, yet remain functional from the user's perspective. So certain parts of your application or your system might have failed, but how can you make these failures transparent to the user? How do you make it unnoticeable so that users actually, they might feel that the system has slowed down a bit, but then after some time it recovers. So you can have some graceful degradation. Or the users don't notice it at all. There are so many failures happening behind the scenes, but as far as the user is concerned, the app works resiliently. So resilience is how you achieve such an outcome. So one of the key fundamentals is trying to compartmentalize failures. So you can, once you compartmentalize failures, what you can do is you can automatically cut off failing components and reintegrate them when they are no longer failing. So you can have patterns like bulkheads and so on, so that failures, the failure of one system doesn't propagate into the rest of your application, right? So these are some of the techniques you can use to incorporate resilience. So let's talk a bit about microservices architecture and resilience. With microservice architecture, building resilient apps become easier because let's take this monolithic app, and you have several components, right? So you may have a component which has a bug, let's say due to some bug there is a memory leak, right? So what that would cause is, it would cause the entire monolithic application to fail, right? So even if it's running on a cluster, it might take down your entire cluster. But if we can break this into microservices, what we can do is the failures will be compartmentalized. So there will be a few microservices that are failing, so you can have recovery mechanisms for that, but the entire system doesn't fail. So if there is a memory leak in a particular component, the microservices that are using that component may fail, but the rest of the system can function, right? So when you bring in other container orchestration systems such as Kubernetes and so on, you can actually, even if such microservices are failing, what you can do is you can do the health check and restart those containers and so on, right? So these are some of the fundamentals that we have to keep in mind. So having spoken about some of the theory, let's look at some of the techniques I'm going to talk about in the rest of the presentation. So I'm going to talk about these patterns. So one of the important fundamentals in Ballerina is don't hide the network. I am sure that you have already heard about this. So in your program, the network calls are easily distinguishable, right? So any interaction that happens over a network has this arrow operator, right? So when you have, when you call normal functions, you might have the dot operator. You have an object and you call a function, and that you just have the normal function call, or you might have the dot operator. But if you look at a Ballerina program, it's clearly visible where the network calls are happening. So those are places where you need to pay attention to. So if a network call is happening, those calls can take longer to execute, right? It's not like code that is running on the same process. And those calls can always result in some sort of failures, right? So as a developer, it increases the code readability, and you can pay more attention to the network-related aspects, right? So that's one of the key design decisions behind Ballerina, bringing in a separate operator for network interactions. So this is what I'm talking about. So we have, as you can see, I have an endpoint, and I'm calling the forward action on that. So this code so this is a network call, right? So we have the arrow operator. But if you look at this particular call, this is a normal function call. So we have a package or a module call log, and we are calling a function on that. So these are local function call, and these are network call. So that's an important distinguishment. So let's look at the first pattern, timeout. So there can be downstream systems which become unresponsive from time to time, right? So the timeout pattern is the simplest resiliency pattern. It basically allows the client to timeout. So you are already familiar with this, right? So when we connect to a website, and if that is not responsive, your browser will time out. And then at that point, we can manually retry, right? So timeout is the most simplest thing, and there are other patterns that build on this, right? So this is a code segment where we are having timeout. So if we look at this code, the important bit is we are declaring an endpoint. So we are going to talk to this particular URL, localhost 8080, and we are declaring the timeout to be 2 seconds. So if that endpoint doesn't respond within 2 seconds, there will be an error. So this is the call that's happening. So we are creating the endpoint here, and then we are calling an action on it. So we are forwarding the incoming request to this particular context. So if this doesn't return within 2 seconds, what happens is there will be a timeout. So let's look at that code. So what I have done here is I'm talking to that particular endpoint. So I have a service that I have declared. So I'm going to call a another service. So the call originally comes to one particular service, and that call is forwarded over to a second service. And like to simulate this failure, what I have done is like I have put a runtime :sleep, right? So if we look at the sequence diagram, so the initial call comes to the first service, which calls the backend client. So the backend client service is this hello service over here. So if I like run that, so I'll run it here. Ballerina run timeout bell. So all this code is in GitHub. So I'll give you the URL at the end of the session. You can actually run everything. So the instructions are also there. So I will call that. So it timed out, and so what we are getting is our client is getting an error. So rather than waiting for 5 seconds, what happened was the call returned after 2 seconds, and that was basically how the timeout works. So the next pattern is, so that was really simple. So the next one is retry. So retry again is like so it builds on timeout. So once in the first case, what happens is like it timed out and it just returns the call to you, and you are supposed to do something. You are supposed to handle the error as a developer. The second pattern is like generally when the network failures are like intermittent failures, right? So when you retry the second time or the third time, you might get a proper response. You might connect to that system. So we have provided the facility for you to incorporate timeout into your client endpoints, right? So that's going to be my second sample, retry. So let's close that. So it's very simple. Again, so this is the interesting bit in this sample. So what we are saying is, so this is the same backend client that I was invoking. So the timeout is now 1 second. So we are saying like retry like 3 times. So the first retry will happen after like 1 second, and then we basically have a binary backoff, right? So we don't immediately so if you want, you can if you give a factor of 1, it will basically try every 1 second. But like we are bringing in a backoff factor so that rather than trying at regular intervals, you basically back off for a period of time, and then you retry. So that's the second sample. So I think we'll look at. So it's again very similar. So we have a call. So this is going to be my curl client. I'm going to call my service. So this call is the call that is going to get timed out, and this is where we are going to do the retrying. So there's a mock service here. So it has some logic. So it randomly, randomly it will introduce a delay, right? So there's a counter, and like every few calls, we are basically like putting in an additional delay. So I'll run that. So I'm going to start that one, and then like curl localhost 9090/retry. So as you can see, this is the backend service that was called. So we are simulating delays. So it got retried 3 times. So this is the first call, second call. On the third call, what happened was there was no delay. So we got a response, right? So the code automatically retried. So that's what happened in that case. So the code here is like the first few calls, there was this output. And then when we kept on retrying, so the client did only one call to this particular, you can think of it as a proxy service, which calls a backend service. The proxy automatically did the retry, and then sent the, when there was a proper response, the proxy sent this hello world response back to the client. So that's the response I got, right? So that's retry. Okay, so that's the interesting bit in retry, right? So we retry, this is the back off factor. So we will retry after like 3 seconds. In this example, the interval is 3000. So we'll retry after 3 seconds, 6 seconds, and 12 seconds, because the back off factor is 2. So the next one is failover. So it's like self-explanatory. So you have a bunch of target endpoints. So when one of the endpoint fails, you basically fail over to the second one. And if the second one fails, you fail over to the third one. And then if the third one fails, you may like come back to the first one and try, right? So that's the failover configuration. So in the failover sample, this is the important bit. So we give a set of target URLs, right? So we have like a mock1, echo, mock. So there can be a bunch of target URLs. And what we are specifying here is based on like these codes, right? So these are like the HTTP response codes, because this is an HTTP client. So if based on like these codes, and in addition to the timeout, we will basically consider these factors for failing over. So if the backend endpoint returns a 501, 502, or 503, or if there was a timeout, what we will do is we will try to fail over to the next one. So it will like first invoke mock1. If mock1 is healthy, we just keep on invoking mock1. If mock2 fails, we switch to echo, and we just keep on invoking echo. And if echo fails, we invoke mock, and so on, right? So now let's go to the demo. I'll show you the code. So I am like going to start up 3 instances in this case. So this is the sample code that you saw in my slide. So it's very simple. It's the same endpoint that I'm going to use. And the way you invoke is again same, right? So as a developer, you declare what your failover endpoints could be. So now that could be dynamic, right? So at the time of programming, you might not know what these endpoints are. So like you may look up, do a registry lookup, or you may load it from a config file or whatever, right? So in this case, I have hard coded it. So then like I have like 2 backend services. So these are like very simple services. We have an echo service here. So these are like simple services. So in one case, there is a there's a sleep, and the other case it's a healthy service, right? So let's start those up. So I need 3 terminals for that. So in the first one, I'm going to start up my proxy, Ballerina run. So I'm starting up my backends there. So they have started up on different ports. So I'm going to now invoke my proxy, which is running on 9090. So what happened was the first unhealthy service got called, right? So there's a 30-second delay. Then what happened was that timed out. So because it timed out, what happened was we got the call basically failed over to the healthy service, right? So if I make another call, it will be the healthy service that is getting called. So now we have failed over to the second endpoint. So it's that which will get called, right? So that's the failover scenario. So on to the next pattern, load balancing. Again, a very obvious pattern. So like you load balance across these endpoints. So the difference between the failover endpoint and the load balance endpoint is, it's just this. You have the target URLs, and then we are just specifying the kind of client that we are going to use. And we have specified the load balancing algorithm, right? So you can have different algorithms, timeouts for these endpoints. So those are all stuff that you have already seen, right? So let's go to the load balancer sample. I'll just close this. Very simple. This is what you saw on the slide. So I have 3 services that I have defined inline in my, in the same file. So these are just dummy services. So mock1, mock2, and mock3 mock services, right? So nothing fancy here. So this is the load balanced service, and then we have the 3 other mock services. So I'll just run that. Clear. Can you guys at the back see the text? Okay, thanks. So the samples are numbered. So once you go to the GitHub repo, it's easy to follow. It's numbered according to the order in the presentation. So I started up that. So I'm going to call this 9090 load balance. So in the first case, okay, mock1 service got invoked. So then second invocation, it went to mock2, mock3, it goes to mock1, and so forth, right? So on and so forth, right? So that's how load balancing works. So as a developer, it's very simple. You just have to declare the proper endpoint. So next one is circuit breaker. So the circuit breaking concept is basically very simple. If a system or a service is failing, you don't want to keep on sending requests to that, and you don't want to allow it some time to recover, right? Because if you keep on retrying and this system is under load or something, you basically don't allow time to recover. So we back off, right? So we back off for a bit. We don't send any traffic over there. And then after some time, we try to see whether that service is healthy and whether we can route traffic, right? So this is the state transition diagram of a failover or a circuit breaker. So in the healthy state, it's closed, so you can route your request directly to the backend. Then there could be certain failures. So immediately, as soon as 1 or 2 calls fail, you don't want to trip the circuit. So you have a failure threshold. So let's say you 20% of the requests or 10% of the requests, if they fail within a given time window, then we trip the circuit, right? So then the circuit goes into an open state, right? So once the circuit goes into open state, it's no longer connected, so traffic will not be routed to the backend service, right? Then after a certain delay, the circuit will go into a half open state, at which point you will send one request to that particular backend and see whether it responds properly. So if it responds properly, then it's successful. You go back into the closed state, and it's the normal state of affairs, right? If that fails, again you go back into the open state, so you will not send any requests again until that particular delay interval. So that's the very high-level idea about circuit breaking. So the circuit breaking sample configuration, so this is the part that you need to pay attention to. So it's a normal HTTP client endpoint. And then we are specifying the circuit breaker policy. So it's a rolling window, and then there are some configurations. So it's easier to understand with this particular diagram here, right? So at any given time, what's happened is the requests that are successful and and the requests that have failed are sort of placed into a bucket, right? So in this case, in the first bucket, so the bucket size is 2 seconds. So this size is 2 seconds. So 3 requests have been successful, nothing have failed. In the second bucket, there's 1 successful, 1 has nothing failed. Here 2 have failed, 5 have failed, and so on. So we basically count the successful and failed requests within a bucket, and then we count it throughout a particular time window. So this is a moving window, right? So once the window moves, we no longer consider buckets that are sort of out of scope, right? So within that particular time window, what we are saying is, if 20% of the requests fail, we will trip the circuit, right? And then it will be in a tripped state for 10 seconds, right? And then again, about the status codes, right? So this is the failover. So you can specify the HTTP status codes, which can be considered as factors for tripping the circuit. And then there's a timeout as well, right? So that's how the circuit breaker configuration works. So let's go to the code. So that's my circuit breaker configuration. I have a backend service where I'm actually again, I'm having a counter and simulating certain delays. And in some cases, I'm sending an error. In some cases, in this case, it's going to timeout. And in this case, it's going to be successful, right? So clear. So I'm starting up 2 instances. So this is the backend, this is the proxy. So the first request succeeds, second request succeeds, and then third request there was an error. So that succeeded, and this is the timeout, so that failed. So here we can see circuit is in open state, right? So we are getting a cached response, right? So let me clear that. So when the circuit is in the open state, what's happening is the backend is not even getting invoked. So you will not see any messages printed here. So we are not sending any request to the backend. We are just sending some sort of cached response. So that's one way of recovering from failures, right? So you have some cached response which is valid for a certain period of time. So rather than hitting the backend on every request, you can send the cached response over, right? So once the time window is reached, so now the circuit went into the open state, closed state again, so we got the proper response, right? So we saw successful, that's printed here, right? So that's the circuit breaker. So finally, let me go into transactions and end my presentation. This is a specification that we have developed, and a bit it's still in so it's not 1.0 yet, it's 0.9. So here the idea is when you have multiple microservices in your system, you need to propagate your transactions. Let's say you started a transaction in one particular instance, you need to propagate this transaction throughout your other microservices. So what happens is, in this case, now these green circles are the microservices. So this is called the initiator. So we are starting a transaction here. So this initiator is now making 2 calls to other microservices, right? So we are making 2 calls to other microservices. And this microservice 2 is calling mu2 is calling mu4, mu4 is calling mu5 and mu6 and so on. So we have each of these services are called participants in the system. So what we are trying to do is we are trying to propagate the transaction context from the initiator right up to all of these participants, right? So in this case, there is a transaction that was started here, and all of these guys are transaction aware, and we are trying to, propagate the transaction. So we have this, we have a process called infection and sphere of control. So when one guy sends a transaction context, what happens is this other microservice is we call it that we say that this microservice has got infected, right? So once it is infected, it can infect others. So it will pass on the transaction context. So this is called the sphere of control. So as long as you keep on infecting others, what happens is your sphere of control expands, right? So it expands, and then finally, this what we have at the moment is a 2-phase commit protocol. All of these participants will participate in a 2-phase commit, right? So this is the 2-phase coordination protocol. So within each Ballerina instance, there is something called a coordinator component, right? So this is now totally, when you go to the code, you'll see that the developer, as a developer, you will not have to deal with all this complexity. So there's a built-in transaction coordinator that's also a separate service that automatically gets started up whenever you have a transaction blocks in your code. So when you initiate a transaction, what happens is it will create a context, right? So there will be a create context. So this coordinator is a single service that is shared by all transaction blocks. So it will create a unique transaction context for you. And then once you are done, so this is your code, you can either commit or abort, right? And at which point the coordinator will take care of running the 2-phase commit protocol, right? So so what happens is, so this is on the initiator side. When you call commit, we will call prepare. The coordinator will call prepare on each participant. So this is sort of a peer-to-peer network. So even on the participant side, there is a coordinator. So the coordinator will basically receive the prepare message with the particular transaction ID, and then it will return either prepared, read-only, aborted. So there are a bunch of stuff. I don't want to go into the details in the specification. And then based on the joint outcome, what will happen is we will either say commit, we will do a notify commit or a notify abort, right? So that's basically how the completion protocol works. So if there is an abort on the initiator side, you simply do an abort, right? So you might, as a transaction initiator, depending on certain conditions, you might decide to abort. So you simply call abort. So that abort protocol is very simple. So let's look at the code. So this is a the initiator code. So it's very simple. You simply have to put the transaction block, right? And then you simply make a network call. So these are the important things. You just have a transaction block. Then you can do your other stuff here. So it's at this point. So this is a network call. So at this point, what happens is this transaction context gets propagated. So the infection happens here. Right? So on the participant side, again, you have like a transaction block. So you are like, in this case, we are annotating this resource saying I can participate in a transaction. So what happens is automatically the transaction context will get available here. So the thing is like to remember if these participants have like, they might do their database calls, they might be talking to other transactional resources. So the transaction gets propagated right down to that level, right? So if one participant decides to abort, what happens, and like the other participants have done database calls, all those database calls will also get aborted. So it's a distributed transaction protocol. So I'll end this with my demo. So I have like 3 services. So we have the transaction initiator. So the initiator basically calls up one participant, and like so the initiator first calls a single participant. That participant, participant 1, will now call out to a different participant, participant number 2. And participant 2 actually does a database update, right? So what I'm trying to demonstrate here is how the transactions get propagated right up to the database level. So let's run that sample. So I'll start the initiator. So I need like 2. So I'll run my participant 1. So now I'm just going to do a curl localhost 9090/initiator. I'm running a bit late. Transaction. So the call came here. Now you can see that we saw a bunch of printouts, system outs on the different consoles. So some of the interesting things are, you can see what happened was, so we initially create a transaction. So this is the initiator. It created a transaction with this particular unique ID, and then the actual network call happened to this particular participant here, which called participant number 2, right? So what happened was these 2 guys now came and registered with the initiator's coordinator as participants. So each of these participants also get their unique ID, right? So once this initiator commits, what's happening is we start a 2-phase commit for this particular transaction ID which we created. So then we are preparing those 2 participants. So when you see that, so you can see the prepare has been received by the 2 participants, and then like they said they are okay to commit. And then what happened was we notified, right? So we notify commit to these 2 remote participants. So then like they received the notify commit, and the transaction was successful. So now let's say like I basically shut down one of these instances, right? So now the transaction should abort. So once I do that, let me show that again. Right? So this participant actually tried to make a call here, and then that failed. So what happened is this guy marked the participated transaction for abort, and then the coordinator was notified, and the coordinator prints this out, remote participant aborted, so the entire transaction gets aborted. So all the participants will get notified saying abort transaction. So that's basically the distributed transaction part. So that's it. That's the end of my presentation. I have the code in GitHub. So Ballerina account 2018 Resiliency. So you can follow the README there. Okay, thanks. Sorry, I took a bit more time.
So Azeez, you've actually finished on time, so that's brilliant. Yeah. So.
Didn't I?
So, do we have any questions? Ah, brilliant. Excellent.
One question regarding these distributed transactions. In these examples, this callback handler for aborting and committing transactions are just logging. But what happens if we have a failure there?
Sorry?
If you fail, for example, to commit transaction,
yeah.
or if you fail to abort transaction inside the handler.
Can you repeat the question for everyone? Here's a microphone.
The question was about distributed transactions.
Okay.
In these examples, these on-commit handlers and on-abort handlers are pretty simple, just logging.
Yeah.
But what happens if we need to do actually something that could potentially fail, like committing transaction, we execute database commit that fails, or we need to notify endpoint which fails? What happens in this scenario?
So I think what you are talking about is like a distributed transaction. So then it gets pretty complicated in such a case. So actually we haven't handled it at the moment. What you could do in those handlers is basically if you have so the database rollback and all that stuff automatically happens. So you don't have to do it in your these handler functions. But what you could do is you could do some other sort of resource cleanup and so on. But if you try to do network calls and all that stuff, those things happen outside the context of this original transaction, right? So, so if you want to do something, then if you try to start a transaction there, that will be treated as a completely different transaction, right? So it won't get sort of attached to the original transaction because the original transaction is now done. I'm just notifying you about some cleanups and all that. Yeah.
No, that's done by that's handled by the two-phase commit protocol. So the two-phase commit is that everybody's ready to commit.
Yeah.
It's ready, so it's saying
yeah.
Commit your transaction.
Yeah.
And one of those participants fails to commit for some reason.
Yeah, so there is a state. So that transaction will have, so that in that case, the transaction has gone into a hazard state. So then what you will get is a hazard outcome. So as an initiator, now you have to now handle that. So we will basically notify you. So transactions can complete in different states. So there is a hazard outcome state where everybody agreed to commit, but then when the notification went, one guy says, no, I can't do it, right? So then you have to, we can't do anything at our level at that point. We hand over responsibility to the developer.
Hello. We saw that we can seamlessly use the transaction with the initiation and the registration. And we saw some calls on the logs. Which kind of channel is used to do that, and is it configurable?
Channels in the sense the communication.
This is we saw. I think it's.
Yeah. So what happens is there are coordinator services that start up on participants and initiators, right? So when you send the transaction context, so along with that actual network call, we piggyback a transaction context header, so which has the callback URL of the initiating coordinator. So then, like as a participant, your coordinator will come and register with mine with your particular callback URL. So at the moment, that works over HTTP. So that bit happens, as transaction context headers.
Okay, so we don't have to open any ports. Imagine we have a firewall between any particular port to communicate.
So at the moment, that port is, so we can configure that port. If you haven't configured that, we basically open up a random available port, right? So but if you have your firewall configuration, you can provide a Ballerina conf file.
Yeah, that's what.
Yeah.
So we did consider this.
Yeah.
We discussed this with Frank during the design of this. And we do have another plan, which we haven't yet implemented, which allows the coordinator to talk, for it to be initiated by the thing. So for example, if we were to use gRPC as the protocol, the coordinator could start up the gRPC call, and then the channel could go backwards, so it would punch through a firewall. But we're not yet there with that implementation. But it's part. I think it's discussed in the spec.
Yeah, there's a bit more stuff to be done in that space. So.
Yeah. Right. I think we better finish the questions. Thanks very much. Very useful. I hope that was a good discussion, and certainly this transaction model. I know it's of a lot of interest to you guys. If you have feedback or input. We're very interested, and Azeez and Frank Lyman, who's at the University of Stuttgart, are the people driving that. It now gives me great pleasure. Oh, let's give a big hand of applause to Azeez.